Hi, everyone. Welcome. We are going to do the final review. First, because we talked about the three-phase system last week, but I didn't give many examples to you. So we're going to review a few examples of three-phase systems, and we will only give you in the final exam. This will be in the final exam, but it will be very similar to this review problem. Also includes the problem that we talked about last week. And it will be a simple one. And I will give you the formula. So please listen carefully. So in this example, it says there are three identical coils. So which 1, 2, 3, and each of resistance 30 ohm and inductance 127.3 millihenry are connected in delta to a 440 volt, 15 hertz three-phase supply. Determine A, the phase current, B, the line current. So when you are looking at, this is what you look at very often, because when we are talking about, if you remember, if you are talking about AC power source, we always mean its RMS value. So 440 volt here, because we know it's an AC signal, it's an AC voltage, so it is the RMS value. And we always mean, when we just say this, we always mean this 440 volt is line voltage. Okay, and what is line voltage? For example, for three-phase system, there are three lines. So because it's in delta connection, there's no neutral line. So it's A, B, and C. And we can just look at one phase, for example, A and B. So A and B, the voltage between A and B, because this is a line, so it's also called line to line, the line voltage, also called line to line voltage. So we know this line voltage between A and B and its RMS value is 440 volt. 440 volt. Okay, and so it connects to the delta configuration, and we define phase voltage as the voltage across the load. Okay, so we call the voltage across load phase voltage, and we define the current flowing through the load, phase current, and the current flowing in the line, we call it line current. So the first thing is we need to calculate the impedance of the load. And since the load consists of a 30 ohm resistance and an inductance of 123.3 millihenry, so the impedance of the inductor is divided by omega Lj. And this omega is in radians per second. So you need to write as 2 pi f. Then f could be put into 50 hertz. So f is in hertz. So f is in hertz. So after I put into a value, it is 40 J ohm. So the total resistance of the load is this, 30 plus 40 J ohm. And because in this problem, it is asked you to calculate phase current and line current in RMS value. In RMS value, so we just we don't need to look at its phase. We don't need to look at phasor. We only need to care about its amplitude. So the amplitude for this impedance is 50 ohm. Okay, and so we have everything. So we have this is 50 ohm, and because it is delta configuration. So if you look at this small voltage between small a and small b, it equals the voltage between capital A and capital B. It means VLIMS equals VPIMS, which means the line voltage equals the phase voltage. So for delta configuration, line voltage equals phase voltage. And it is written in phasor, but you can also write a scalar. So it automatically it has VRIMS equals VP RMS. VP RMS. RMS. So when I put a bar on the top of this variable, it means it's a phasor. So, and then the next step is we want to calculate the phase current. So right now you know the VP, right? Because this VPIMS equals VLIMS equals 440 volts. And we also calculate the amplitude of the impedance. It's 50 ohm. So the IPIMS, so this phase current equals the phase voltage divided by the amplitude of impedance. So that's also the reason that we when we perform the AC analysis, we tend to use its IMS value. Okay, because if we use IMS value, then its calculation is the same as a resistor. So we have VPIMS divided by the amplitude of the impedance of the load, and it equals the IMS value of phase current. So it's 440 divided by 50, but the phase current is 8.8 amp. Okay, so this is the phase current. The phase current is defined by the current flowing through the load. So this is the flows through the load. Okay, and then the second problem is it asks you to calculate the line current, which is the current flowing through the line. And in last week, we proved that for a delta configuration, its line currents and phase current has this relationship. So we have this this is the phasor of line current equals the phasor of phase current multiplied by square root of 3 and minus 30-degree phase angle. So, well, because we just talked about it last week, so in the exam, I will give you this. I will give you this formula, and we're not going to prove it now because we have proved this last week. And so because in this problem, I just asked you to write the answer in IMS. So we don't need to look at the phase. So in this case, it means the amplitude of the line current is the amplitude of the phase current multiplied by square root of 3. Okay, so once we find out IPIMS, the IMS value of the phase current, and then we multiply by square root of 3, and then we can get the line current in IMS. The line current in IMS value for this system. Okay, so this is once you got the phase current in IMS and then multiply by 3, and you have the line current in IMS for this delta configuration. Okay, so that's the characteristic of a delta configuration. So for a delta configuration, the phase current, phase voltage equals the line voltage. Okay, so it can be easily determined by this because small a connect to capital A, small b connect to capital B. So we know the voltage between small a and small b equals the voltage between capital A and capital B. And for the line current and phase current, because last week we applied KCL at node A, because there's also a current flowing in this direction. There's also a current flowing into this direction. So their current are not identical. IL and IP are not identical. And last week we proved that we proved this before. IL equals IP multiplied by square root of 3 and minus 30-degree phase angle. So this is how we calculate the phase current, phase voltage, line current, and line voltage for a delta configuration. And this will be in the exam. Okay, so we talk about the next problem. So next problem is a similar one, and it just compare the this we call the Y configuration or star configuration and delta configuration. So suppose there's a 3 ohm resistance and a 4 ohm inductance. So it means its load ZL is 3 plus 4 J ohm. It has a real part, it has an imaginary part, and it is they are connected in star. The star here means Y configuration, and second in delta configuration to a 415 volt. This is VL RMS. This is the line voltage in RMS value. 3-phase supply. Please calculate A, the RMS value of line and phase voltage. B, the RMS value of line and phase current. Okay, so we are doing the same thing. Since you are only be asked about the RMS value, so we don't need to care about the phase. Since we don't need to care about the phase, we calculate the amplitude of the load. So the amplitude of the load is 5 ohm. And then you draw the configuration. The first one is star, or we can say Y configuration. So you draw the Y configuration, and there's a neutral line. Neutral line is in dot because if they are perfectly balanced, if the loads are the same and the 3-phase voltage are the same, so we can remove the neutral line. But we put a dot line here. So this VLRMS 415 volt, it means line to line voltage. So we can put positive, negative here, but since it's AC, so its direction is changing all the time. But for clarity, we can have a plus and minus. So we know this line to line. So this is line to line is 415 volts. And so in this case, so this is the phase voltage. We look at A. The phase voltage of load A, of this load, is the voltage across this load. And this is a phase voltage, VPRMS. They are not the same, right? Because they do not connect to the same starting node and ending node. But if we look at the line voltage, line current means the current flowing through the line. And the phase current means the current flowing through the load. And in this case, it goes back through neutral line. And although the current in the neutral line will be canceled, so there's actually zero current in the neutral line, but that's how it forms a loop. Okay, so we know for the Y configuration here, for Y configuration, and the line current equals phase current. Okay, and the line voltage is equals the phase voltage multiplied by square root of 3 plus 30-degree phase angle. So, well, to help you memorize this, so if you draw, it's either you can draw. You may be asked either in Y configuration or delta configuration. Once you are asked about one kind of configuration, then you draw this shape. And then when you finish this shape, you will figure out there's at least either current is the same or voltage is the same. In this case, the current, the line current and phase currents are the same. And the other left is the voltage, and the line voltage is always larger. What happens in line? As long as they are different, what happens in line is always larger. So in this case, it's voltage difference, and the line voltage is larger than phase voltage. So the relationship is VL equals VP multiplied by square root of 3, and the phase angle is plus 30-degree. And then, well, you don't need to memorize this because this formula will be also be given. And if we go back look at if we go back to look at the delta configuration, you will find out that for delta configuration, VL and VP, they are the same. So the current, the phase current and the line current are different, and line current is larger. So line current will be the phase current multiplied by square root of 3, but in this case it's minus 30-degree. So it's easy to even though you are not given this formula, it's easy to memorize it. And then we derived this formula last week. So if you are interested, you can look at the proof that we talked about last week. So, but we continue to look at this problem. So, problem A, we need to calculate the RMS value of line voltage. So, well, the RMS value of line voltage, it is given, right? Because when we are given a voltage, we know it's an RMS value, and we know it's a line-to-line voltage. So line voltage VLRMS equals where we are told, so 450 volt. And for phase voltage, and they are different, so we resort to this formula. And so the phase voltage in RMS equals the line voltage in RMS divided by square root of 3. And the answer is 240 volt. So any questions regarding this one? So we answer problem A, and then we look at problem B, where X the same thing, line current. Oh, not yet. Yeah, we're X about line current and phase current. So we have this line voltage and phase voltage. So since you calculate the phase voltage, and then you are told about ZL, right? So we can calculate the amplitude of ZL. And so the phase current is just phase current. So if you look at this, phase current, VP RMS, just equals VP, the phase voltage, IMS divided by the amplitude of the impedance of the load. Okay, so once you find out, and then you are able to calculate this just as what I just did. And then since for Y configuration, ILIMS equals IPIMS, right? So since we calculate IP phase current already, so we know in this case in Y configuration, its phase current will be equal to line current, and which is 48 amp. Okay, so and it is also asks us about the delta configuration. So when it is in delta configuration, same thing, we write a delta shape and we mark A, B, and C, and then it is asked about the phase voltage. So in this case, phase voltage VP-IMS equals VL-IMS equals the line voltage. So we could easily write it down. VP-IMS equals VL-RMS equals 415 volts. And regarding the line voltage, yeah, the line voltage is given. The line voltage is given by the problem. It's 415 volts. Okay, so right now you're asked about the phase current and line current. So for phase current, because we already know the phase voltage in IMS, so the phase current in RMS is simple, right? You just need to use VP-RMS, the phase voltage, divided by the amplitude of the load. Okay, so yeah, so the same thing divided by the amplitude of the load, and then we can calculate about the line current following the formula. So since the phase voltage equals, and the line current is square root of 3 times larger than the phase current. So we have the phase current in IMS value multiplied by square root of 3 is 83 times square root of 3, which is 144 amp. Okay, so the line current here, IL-RMS is 144 amp. And so one thing we can notice, so we are this Y configuration and delta configuration, they are connected to the same load, which is 415 volts in RMS value. But when loads are connecting in delta configuration, it generates a large line current comparing to Y configuration, because if the load is in Y configuration, it only generates 48 amp line current. But for delta configuration, it generates 144 amp line current, which means in delta configuration, we need to have a thicker transmission line. So it increases the cost. And also, if these 3 loads are the coil of the motor of a 3-phase motor, and then if it is connecting delta configuration, because when motor starts, because of the resistance, because of you need to conquer the static friction. So when you start a motor, it generates the large current. And if it is in delta configuration, this current will be even bigger and it may damage the circuit. So for a huge motor, when we start a large three-phase motor, we will use Y configuration first because it generates a smaller line current. And then when it runs in steady state, and then we switch back to the delta configuration. So for large motor, this is what people usually do. So when loads are connecting in delta, even though they are the same loads, a larger line current is taken from the supply compared to a star configuration. Okay, so this is their difference. Okay, and so for three-phase system, this is the type of questions you will be given in the final exam. And one more thing we need to mention is the power of the three-phase system. So let's look at this. Okay, so the 12 ohm resistors are connected in star. Also, star configuration is equivalent to Y configuration. To a 415 volt, this is VLIMS. So we just write VLIMS down. Three-phase supply. Determine the total power supply by the resistors. Okay, so we just need to look at one phase. So the resistor is 12 ohm. So if we are able to calculate the current flowing through the resistor or voltage across the resistor, we can calculate the power, right? Because but in this case, because we just proved that we proved this actually. The real power is the phase voltage in IMS times the phase current in IMS times cosine theta. We just proved this for a single load. For a total load, you need to multiply by 3. Okay, because we just talked about this last week, so this formula will be given, although this is a simple one. Okay, so we need to calculate. We are given line voltage, and we need to calculate the phase voltage in IMS. So we look at the formula for Y configuration. So you are given line voltage, and you need to calculate the phase voltage. So we have phase voltage equals the line voltage divided by square root of 3. And then we don't need phase here. So VPIMS equals, I can write it here. It's VL RMS divided by square root of 3. Square root of 3. Okay, this is from the formula. Okay, equal. So, and then which is this, and then I write it here. So this is VPIMS. This is VLRMS. VLRMS divided by square root of 3. Okay, and then since we have VPIMS, we calculate the phase voltage, and we know the resistance, and then we can calculate phase current by using Ohm's law. So by Ohm's law, the phase current in IMS equals the phase voltage in IMS divided by the amplitude of the impedance. And in this case, it's a real number because it's just a resistor, so it's 12. So 240 divided by 12 is 20 amp. So once you calculate the phase voltage and phase current, then by applying this formula, and then theta is theta V minus theta is the phase angle of the impedance. phase angle of the load impedance. And if you forget this, please go back to the notes. And so, so we can calculate the power for a single phase, which is VPRMS is 240, IPRMS is 20 amp, and the phase angle of the load, because this load is a resistor, is a real value, so the theta equals 0, and it's 4,800 watt, which is 4.8 kW. So this is for a single phase. And since it has 3 phases, so the power need to be multiplied by 3. So total power, it need to be multiplied by 3. So regardless of the Y or delta configuration, because once we calculate, so the only thing we need to care is to calculate VPRMS. VPRMS is the voltage across the load, and we calculate IPRMS, and then we don't need to care if it's Y or delta, as long as we know the phase voltage and phase current, and then we can calculate the total power. Okay, so for both Y and delta configuration, once we have the phase voltage and phase current, then we can apply that formula to calculate the total power. Okay, and it is the true power. Okay, and if we want to calculate this true power, so this is also called true power. This is true power of real power, right? And the real power can also be represented by line voltage and line current. Okay, so this is the true power formula for phase voltage and phase current. And so if you want to convert to line current, for example, so for the case of Y configuration, so what happens for Y configuration? So for Y, we have, for Y configuration, we have VL equals VP divided by square root of 3. Because we don't need to care about the phase. Because we are talking about IMS, I just write IMS. We have VL IMS equals VP IMS multiplied by square root of 3. And we have this Y configuration. We have IL RMS equals IP RMS. Okay, phase current equals line current for Y configuration. So if it is a Y configuration, then if we want to convert this VPIP to VLIL, and so VP, so we have this IL, IP equals IL, and VP, so we have VP RMS equals square root of 3 VL RMS. Okay, so you have this square root of 3. So VL VP, wait, VP multiplied by, okay, VP multiplied by square root of 3 equals VL RMS. And so VP, okay, so if you want to convert to VL, so you have this. VP is replaced by VL IMS divided by 3. So if you replace VP to this VL, this equation will become square root of 3 VL IMS times IL IMS times cosine theta. So if you want to calculate the total power in terms of line current and line voltage, then the formula becomes this one. The formula becomes this one. Okay, let me make it more clear. The formula becomes this one. Okay, so we can double check. So for the line voltage here, so since you have phase voltage, you just calculate phase voltage. We have phase voltage is 240, and then line voltage is 415. Okay, so we calculate the power in terms of line voltage and line current. So line voltage is 415, and line current equals phase current, which is 20. And the answer is, this is square root of 3 times 415. Wait, let me double check. Let me double check. So the line voltage in IMS should be voltage 415 should be. Let me double check here. So square root of 3 times 415 times 20. Yeah, it's correct. It's 415. Please make correction, because the line current in the line voltage in IMS value is 415. Okay, and the line current in IMS for this what configuration? For this Y configuration is 20, and the answer is correct. Okay, and this is true power. Okay, and if you want to calculate the reactive power, the total reactive power, and it will be, let me change this. Let me change the what's in my notes. And all right, and so we have the total true power, and if you want to calculate the total reactive power, just multiply by sine theta. And if so, we have 3 times VPRMS phase voltage in IMS times phase current in IMS times sine theta. This is the total reactive power of a 3-phase system, regardless of if it's line, regardless of Y or delta configuration. And if you calculate line voltage and line current, then the coefficient of 3 becomes square root of 3. Okay, so, and we also have total apparent power. And so if the same thing, if you are given phase voltage and this phase current, it is 3 VPIMS times IPIMS. And if we are using this line voltage and line current, it's square root of 3 times VLIMS times ILIMS. Okay, so this is how we calculate the power of either Y configuration or a delta configuration. Okay, so that's how we do it. Okay, in this example, I prepared another example regarding how to calculate the power. So in this example, it says there are 3 coils, and each with the resistance wait, let me. Okay, and 3 coils, each with a resistance of 10 ohm and inductance of 42 millihenry. Okay, are connected to 1 in star or Y configuration, B in delta configuration to a 415 volt, 50 hertz, 3-phase supply. Find the total power dissipation in each case. So bad. Okay, and in this case, first we need to calculate the impedance of the load. So the load consists of a resistor and an inductor. Okay, so since we got 50 hertz, we also got the inductance. So this is 13.19 J, and we have Z total is represented by this. And we just need the amplitude of the phase, which is 16.55 ohm. Okay, so this is the amplitude of the phase. And, and for the star configuration, we draw the shape of the star configuration, and then we just need to calculate phase voltage and phase current, or line voltage and line current. So how about we look at phase voltage and phase current? So since it's Y configuration, it should have a virtual neutral line. And then so for VL and VP, for the phase voltage and line voltage, we have this relationship, right? So phase voltage is smaller in Y configuration. So it is VLIMS divided by square root of 3 is 240 volt. And since we know the phase voltage and then divided by the amplitude of the load, it will be the phase current. So once we find the phase voltage and phase current, then we can apply the total power formula, which is 3 times VPRMS times IPRMS times cosine theta. And theta is the angle, phase angle of the load. So let's look at the previous slides. The phase angle of the load is 52.83 degrees. And so this is theta is the phase angle of the load. If you have doubts, you can go back to the notes that last week to see the proof. So theta is the angle of the phase angle of the load. Okay, and then you got this total power, and it's true power or real power. Okay, and so in Y configuration, it's line current equals phase current equals 14.5 amp. Okay, this is the power, total power of a star configuration. Okay. And let's calculate the power, total power of a delta configuration. Same thing here. We calculate VPRMS and we calculate IPRMS. Once we have phase voltage and phase current, and then we can apply to this formula regardless of its Y or delta. So for the phase voltage, so if it's in delta configuration, then the load shares the same voltage with VL. So, but the phase voltage equals the line voltage, which is 415 volt. This is given by the problem. And since we have this VPRMS, we have phase voltage, and we also know the amplitude of the load, and then so we can calculate the phase current. And once we have the phase voltage and phase current, and we also know the phase angle of the load, and then we can apply this formula. So this is 3 times BPRMS times IPRMS times cosine theta. This is the total true power or real power of this delta configuration, and which is a constant, right? Because for the power of a 3-phase system, it is a constant. And so what's this? It's this larger than Y configuration. Yeah. Okay. So the power of delta, because the line current of a delta configuration is larger than Y configuration, and its power of delta configuration is larger than Y configuration under the same line voltage, right? Because so you can compare the result to A. Okay, so compared to result to A is just a 6.3 kW, and but if it is counted in delta, and it becomes almost 3 times larger than Y configuration. Okay, so and also in delta configuration, the line current is also larger than the line current in Y configuration. Okay, so that's we finished the review of this 3-phase system.